Hello guys, welcome to Embedded System. Now in this lecture we are going to revise the last lecture in little bit, which is nothing but the characteristics of embedded system, and then we're going to study the types of embedded system. In this lecture I'm going to show lots of hardware, right? Those belongs to a various different types of embedded system. So let's get going. Okay. So first of all, let's talk about the last lecture, which is characteristic of embedded system. Now we have seen the characteristics in a lot of detail. So just revise this. So these are the key characteristics of embedded system, which says it should be a task specific. First thing it should be a very much task specific. That means it should perform a given task like very particularly with a high stability and high reliability. Also it should have a high efficiency, right? It should be a time specific as in context to our real time embedded systems, right? In case of real time embedded system, this parameter is very much important, right? It should have a minimal user interface, right? These 2 points are a lot of connected. If we keep a high user interface, then it may need a large power. Like in mobiles, if we have a bigger screen, it consumes much more power and your battery life will be less. So we need to put a bigger battery. It ultimately increases the cost, which is nothing but our next key characteristics. So while designing the embedded system, we have to keep track of all these parameters. Then only we'll be able to develop a proper and I can say commercially viable embedded system, right? So this was the revision about the last lecture. Now let's go and talk about the today's lecture. The today's lecture talks about the types of embedded systems. Now here you see we have uh, different type of embedded system which is based on the functional requirement of an embedded system. Now based on the functional requirement, we have real-time embedded system, we have a standalone embedded system, we have network embedded systems, we have mobile embedded systems, right? Now let's see the example one by one, and let's see how the real-time system can be. It can be a small scale, it can be a medium scale, or it can be a sophisticated embedded system. So these types can be of this type, right? So either real-time system can be of these three types, even standalone system can be of a small size or a medium scale or a sophisticated. A network embedded system can be a small scale, medium scale, or sophisticated embedded system, right? Further, same about the mobile embedded systems as well. So this is a board from a Freescale, right? You can see the name, Freescale Semiconductors. This is based on their own customized processor, and this board is used to develop they are used to develop and robots which are having a real-time performance for obstacle detections, for path finding, and all those things, right? So this is a pretty much heavy board, I guess, and having a lot of computational power. We can attach even a camera to this board. So basically the functionalities of real-time embedded systems are: a system should be able to provide its output within a provided time frame. Otherwise there can be a very much catastrophic effects or hazards because of its delay, right? For example, if we use this board to develop a robot, let's say an obstacle avoidance robot, and if this board provides output after some time, that means it a delayed output, then it won't be able to avoid the obstacles, it will go and hit the obstacle. So that's nothing but a failure of a system. Similarly, if considering another example, let's say ABS, that is anti-braking system, uh, is used, the embedded system used for ABS, if it provides a delayed output, then there can be an accident. So overall, if the delay generates in real-time embedded system, then it is nothing but the failure of an embedded system, real-time embedded system. So we have to take care of the time constants as far as real-time embedded systems are concerned, right? Next is standalone embedded system. Now standalone embedded system is something like something like this board, right? Now this board is from the Atmel, which is X Mega. These are Atmega X uh, AVR X Mega boards, right? This is the evaluation board I got from the supplier. Now you see there are onboard buttons, right? And onboard chip is there, onboard microphone or onboard speaker is there. There is a light sensor, right? There is onboard memory. This is the processor X Mega, which is the 16-bit microcontroller, right? So these are all the components on board, and it does not need any kind of computer to work on, right? Once we put the code in this embedded system, it can work by its own, right? So the definition or the key characteristics of a standalone embedded system is, if an embedded system works by its own, or we can say if it does not depends on any computer for its working, then we can say the embedded system as a standalone embedded system. For example, your mp3 players, your digital cameras, video game consoles, those are nothing but the standalone embedded system that does not need any kind of computer or computer assistance for working, right? So these are kind of the standalone embedded systems. Now let's go and see the next let me give you some more examples for this. A kind of data logger systems. If you see a data loggers like temperature data logging system, humidity data logging systems, those all come under this uh, standalone embedded systems, provided they should not be depend on any networking conditions, or providing it should not depend on a Wi-Fi, WLAN or any kind of internet connection for their working. Okay, so if an embedded system depends on LAN, WAN or internet or some kind of a network, then that embedded systems are called as network embedded systems. So that was our next type in embedded systems. And embedded systems, if it depends on a network for the resources, then the system is called as network embedded system. For example, and embedded systems developed using ESP8266. Now this embedded systems needs a Wi-Fi connection to provide an output. Let's say I have developed a temperature data logger using this, and this temperature data logger sends output to a particular server. So I have at home a several such kind of temperature data loggers along with humidity data loggers. I have used IoT server along with display board and database. In the background, I have used InfluxDB database along with the Grafana for displaying the details about. So these are nothing but the server requirement, and this device needs a server for its working, and that's why we can call such embedded system as a network embedded system. For example, your home security or home automation services, for example your like home assistant systems, those who control the light, your TV, ACs and all those things in the home, that depends on the network inside your home, and that's why we called it as network embedded system, right? After that, the embedded systems, those are very much portable. For example, your mobile phone or this device. We made this device using. Let's not discuss the internal components because this is currently in development. This device, let me tell you, this is a very proud moment for me as well as our college. Triple IT in Nagpur, AIMS Nagpur and IIT Jodhpur combinedly developed this device for tracking COVID patients. Right? This device is able to retrieve the vital parameters from the COVID patient, and this is used to keep a track on him. Right? So this device works independently. This is very much portable. Like I develop all the hardware and the programming inside this device. This is very much portable. It is having battery life. It is having proper information sensing, that means proper sensors and all those things inside it. So this is very much portable, and that's why I can call it as a mobile embedded system, right? For example, your mobile phones itself a good example of a mobile embedded system, but nowadays the mobile is having too much more features other than just having a call and SMS, and that's why it is sometimes not considered as a embedded system. It is kind of a computer and mouse division. So we have seen computer is not embedded system, but mouse is embedded system. So kind of differentiation is there. So that's what like the division of embedded system based on its functionalities, right? Again, one thing we should add in this: such devices, such mobile embedded systems have limitations of a battery and memory, right? So we have to take care of such things when we develop mobile embedded systems or portable embedded systems, right? So let's go and now talk about the division of embedded system based on the performance of a microcontroller. So there can be a small scale embedded systems, there can be a medium scale embedded system, or there can be a sophisticated embedded systems, right? So let me tell you, this device, even this device, those this is the category of a small scale embedded systems. Now this is having a 8-bit microcontroller. Sorry, it is having 32-bit microcontroller inside this, but the functionality is very much limited because of its um, like the features available with the microcontroller. So this is a kind of a small scale embedded system. This is also having a small scale 8-bit 32-bit microcontroller inside this, and that's why this is also a small scale embedded system. Even this is also a small scale embedded system, right? But when we talk about this board, this comes under a medium scale embedded systems. You see, the configuration and the software complexities required to program and to make work with this board is quite larger than compared to these boards, right? So this is comes under the medium scale embedded systems. Now let's talk about some sophisticated embedded system. Let me show you a next board. Let me unpack here. Now this board works on the RTOS, right? The real-time operating system. We need to put real-time embedded system into this board, right? We have to program this board using a real-time embedded system. There is a kind of brochure and all those things inside this. So you see, this is AVR Atmel AVR 32 board. It is having 32-bit microcontroller along with the memory, the crystal, even a small joystick is there. I hope you are able to see. This is a joystick, a small joystick is there. All having a batteries, a variable port. This is the variable port, LCD screen, all type of DB9 connectors, right? DB9 connectors, gigabyte port, power jack buttons, right? And on this side also in external right, a memory here, right? And we work by putting this memory card into this, right? And we can have a SD card into this, which contains its like external hard drive, right? This is another port which is used to connect camera called as Nexus Cam and all those things. So this complexity for developing an embedded systems with such kind of a board is tremendous, right? We need to have a sophisticated SDKs. We may need to use the IP or intellectual properties of different companies, if we have heard about the engine control unit, we called it as ECU. So ECUs generally contains a communication board bus called as I2C. That I2C is developed by a Bosch, and we have to use that bus for particular ECUs. That means we are using intellectual properties of Bosch company. Another thing with the sophisticated embedded system is that we may not have the tools or the programming devices or development tools that may be needed at this instance. So we have to start with a scratch and develop such systems. This is merely a example of sophisticated embedded system, but the actual sophisticated embedded systems are much more complex than this. Okay, whereas this is the medium scale embedded systems, in which, right, we may need to use application specific standard products, for example such controllers, right, some modules and fuse bits, some memory chips, Along with that, we may need to use TCP/IP protocols. We may need to use RTOS even, and we may need to use a simulator, debugger, and integrated development environments for this. So basically, the complexity increases as we grow from small scale to sophisticated embedded systems. For example, we may have available C code libraries, we may have available diagrams or available like we can say code snippets for developing 8-bit microcontroller system, or we call that small scale embedded systems. But if we move towards the medium scale, the complexity increases. Some things we can use like IPs or application specific standard product, or we call it as ASSP, or like TCP/IP protocols and all those things. But as we move towards this one, we may not have things available on our hand, and we may need to start from the scratch. So this is how the division of embedded systems are there. So let's revise once again. What are the embedded systems? How many types are there? So basically there are 4 types, right? Basically there are 4 types, and those are real-time embedded systems, standalone embedded system, network embedded system, and mobile embedded system. Each of this type can be of 3 types, which is a small scale, medium scale, or sophisticated. So this is all for the division of micro embedded systems. We will continue with a specific type, that is real-time embedded system, in the next lecture.